Welcome to a second entry in Today on Math Reddit. As I mentioned in yesterday's debut, this is how I'm managing to keep myself entertained for a while as a newly retired math professor with, I guess, too much free time on my hands. So I've scoured Ask Math and learnmeth and come up with a handful, 3, math questions that are in that algebra to pre-calculus to calculus range where I'm most comfortable. And I'm going to give you some answers and discussion about those topics. As I mentioned yesterday, people will have answered these already in the subreddits, right? So I'm not pretending that these are the best answers. To me, this gives me an opportunity to perhaps do a little bit of extra discussion about what circles around these problems, give some tips and strategies, and maybe just seeing something in a visual form makes it easier to understand what's going on for some people. Okay, so we've got one question that's pretty much just basic manipulative algebra, something that dips into the limit definition of the derivative for Calc 1, and something that involves a little bit more sophisticated manipulative algebra and the quadratic formula. These are not in order of increasing complexity. They're just the order in which I came across them and whipped up some slides. Okay, so problem number 1 from the user Bellalelogram. That's a cool name, on our Ask Math. And this is just some basic manipulative algebra, but it's good to review these kinds of things. The problem that was posed was to take the expression z equals b over sigma times the square root of n and solve that for n. So this is a story just about solving for an unknown when that unknown is buried inside a whole bunch of nonsense. How do you extract it? So the way to think about it is that this n is in math jail, and we need to break it out. I see this as what I call the onion principle. We need to peel away the layers that are keeping us from freeing n out of math jail. So for this particular expression, in order to free n from math jail, we have to peel off the b, we have to peel off the sigma, we have to peel off the square root, and we have to do something about the fact that n is in the denominator. The big thing to remember about algebraic manipulations is to not be intimidated by the choices you have to make. Who is in charge of this equation when we're working on it? We are in charge of this equation. So if we want to do something to this equation, like peel off that capital B, then damn it, we're going to peel off that capital B. The thing is, we have to do it properly. Okay, so I'm going to repeat that mantra a few times. We're in charge of these things. We can multiply by anything we'd like as long as we multiply both sides of the equation. That equals sign is ironclad gospel. We cannot do anything that's going to break the equality. But other than that, we might be good to go. We can divide by anything we would like to, except for 0, right? We're not that powerful. But we have to divide both sides by the same thing to maintain the equality. If we look at one expression and decide, you know, it'd be great if we could flip this thing upside down or find its reciprocal, well, we can flip it upside down as long as we flip over both sides of the equality to maintain the equality. We can raise things to any power we would like. Now, there we get into issues of negative things not being defined when we raise them to certain exponents. We're not going to go there. Generally speaking, if we want to square something, cube something, raise something to the 4th, fine. We can do it as long as we do it to both sides. We are powerful. We are in charge. We can do anything we want. The other way to look at this is like a puzzle game. Remember that you play this at like restaurants as a kid? There'd be like a little square with these like a grid of 9 or 16 little tiny square tiles, but one was missing and you had to move things around in order to form the right picture. This is sort of like that as well. We need to move tiles around in order to jailbreak the n from its math prison. So how are we going to think through this? Well, first of all, we're trying to solve this for n. We're trying to jailbreak the n. So boy, it would be nice if n wasn't in the denominator. Okay, well, who's in charge of this? We are. which means if we want to flip over that right-hand side, damn it, we can flip over that right-hand side. We just have to flip over both sides to maintain the equality. So we flip over z, we got 1 over z. When we flip over the right side, now we've moved the n to the top. Well, what's next? Well, there's lots of choices, but given what we have, look at that right-hand side. Boy, it would be great if we could multiply that right-hand side by capital B, because then it would be gone. We'd be one step closer to jailbreaking the n, right? Well, who's in charge? We are. And if we want to multiply that right side by b, damn it, we can multiply that right side by b. We just have to multiply both sides by v. And similarly, it would be great if we could divide both sides by sigma or multiply by 1 over sigma, right? Same thing. It's okay. We can do that as long as we do it to both sides. So if we take this expression as it stands, multiply both sides by b, and multiply both sides by 1 over sigma, we will have almost completely jailbreaked n. We'll be left with the square root of n on one side and just a whole bunch of stuff on the other side. And if we're taking this expression that's a bunch of stuff equals square root of n, and we're trying to jailbreak n, we got to get rid of that square root. How do we get rid of a square root? We can square both sides. Who's in charge? We are. Okay, so if we square both sides, we're going to end up with the square of what used to be on the left-hand side equals n, but that's of course the same thing as n equals that stuff. And so ta-da, we have completely done a jailbreak for n and we've solved for it. Now go back and follow the details of this to see if you can come up with what would be the final expression for n. But that's the overall idea. All right, let's jump to calculus. And for those of you that aren't in calculus yet, maybe you want to watch through this, A, because there's no pressure because you're not the one doing it, right? But B, it could give you sort of a sneak preview of some of the things you'll need to think about, and you might look at some of this stuff and go, hey, that's not so bad. So the user SpeedyProYT on the LearnMeth subreddit, Reddit, was given a problem that boiled down to finding the derivative of f of x equals 3x squared plus 2x plus 1 using this structure, f of x plus h minus f of x over h. Okay, this is leaning to the limit definition of a derivative. But here's the background. The reason I picked this is because it's fun to discuss what's actually going on here. Okay, so this expression, f of x plus h minus f of x over h, that is just a more detailed form of something that looks like delta y over delta x, right? When we take x values and plug them into a function, we get the corresponding y value that would go on the graph at the point xy for this function. So this is just the difference between two adjacent functional values on this graph. So delta y over delta x. H will make more sense when I show you a picture in a minute. But if you understand that f of x plus h minus f of x is certainly a delta y, then you're halfway there. Okay, what this thing is it's measuring a slope. H is the distance between one point on a graph, and then we're just going to inch over a little bit on the x-axis to another point. So like from 1 to 1.5. Okay, h is the distance between those two things. So we're measuring a delta y over delta x. We're measuring a slope. This structure is called a difference quotient, and it gives the slope of a line between two points that are attached to a graph. So f of x, that's an xy pair, one point on the graph of this function. And if we start at x and we just inch over a little bit to x plus h, and then we find a new functional value, now we've got this point and this point on that graph. The straight line between those 2 points has a slope, and this expression is calculating that slope. Delta y over delta x. X plus h minus x is h. That's delta x. Now, the way this turns into calculus, and not just an exercise in finding slopes of lines attached to a graph, is that we're going to ask the question, let's say we got a thumbtack here at this point on the graph, and then we inch over on the x-axis to the second point. And we got these 2 points here, and there's a straight line between them. What if we inch this x-coordinate a little bit closer, a little bit closer, a little bit closer, a little bit closer? As h goes to 0, what's happening to the slopes of these lines that we're creating as we form that process. Okay, here's a picture instead of me doing this with my fingers, right? So imagine this point at 0, 1, where all these lines are converging. Imagine that's our thumbtack. And we have a little piece of string. And we take that string and we thumbtack it to the curve up here at point A. So these 2 points are landing spots on this curve, but now they're connected by this straight line. That straight line has a slope, right? H is the distance horizontally between those 2 points. Now let's lift up that thumbtack and move it to this point. We've now made the line B. That has a different slope than the line from A. And the distance between the x-coordinates has gone from this much to this much. Then we pick up this thumbtack and move it to this point and pin it down. And now we have this, the string is now forming line C. So we've adjusted the slope a little bit more, but even more importantly, what used to be the distance this big between those 2 points out to point A has gone to this, to B, and then for C, it's gone to this. And then we're going to do it one more time to D. And this, so what's happening is that as this point gets drawn back to collapsing on the thumbtack here at 0, 1, we're generating a bunch of lines that has, you know, one slope, another slope, another slope, another slope. Imagine this second point eventually collapsing back onto this one. We should be able to predict what the slope of that line is going to be. And that's pretty cool, because all your life you've been told you need to know 2 points on a line to generate the slope. This is giving us a trick to discover the slope of a line attached to a function at 1 point. And that's a pretty significant conceptual jump. But that's what's happening with all this f of x plus h minus f of x over h. Now, if you understand that or not understand that, it still just turns into a bunch of algebra to get it done. Now, the question that was asked, this is not the user saying this. This is the way it was posed as a problem to the user. Should have been written as determine the derivative of this function by building and evaluating f prime, the derivative, is the limit as h goes to 0 of this difference quotient. So this is the process of taking these points and watching what happens as these points collapse to that unifying point down there. Now, this curve is not the specific function that's in the problem. It's just a generic picture, but it's the same story. Now, how do we evaluate this? Well, we just build this thing and then ask what happens as h goes to 0. So at this point, it's algebra. So f of x plus h, well, if x is 3x squared plus 2x minus 1, f of x plus h is 3 times x plus h squared plus 2 times x plus h minus 1. Let's expand those terms, and there's really not much that's going to happen to them. But that's okay, because that mess is only this. To build the rest of this numerator, we're going to subtract the function itself. So here is f of x plus h. Here is the original function. When we subtract those to make the numerator of the difference quotient, look what's going to happen. The 3x squareds are gone. The 2x's, gone. The minus 1 and the minus 1, gone. The only terms that are going to survive are the 6xh, the 3h squared, and the 2h. Every surviving term in f of x plus h minus f of x has an h on it. And so what happens when we construct f of x plus h minus f of x over h? Some of those h's cancel out. And then, with what's left over, we can play the thought experiment. What happens if h becomes 0? What happens as that second point on that graph, I should be going this way, collapses back onto that first point? What is the tendency of the slopes that we're making as those 2 points collapse together? Okay, if you follow through this algebra of taking this f of x plus h, subtracting this f of x, taking the result, dividing it by h, and then saying what happens when h goes to 0, you should end up with 6x plus 2. Okay, so make sure you can get that. All right, finally, out of calculus back to just some quadratic formula stuff. But this has a couple of steps in it that are somewhat sophisticated, and it's awfully alphabet soupy. Okay, so to me, it was a good example to go through. Here's how the question was posed from the user Ealing Potato on our askmath. I was wondering if that was supposed to be eating potato with a typo. Who knows? I don't know. You'll have to ask that user. If the solutions to the equation mp squared plus bp plus k equals 0 can be written like this nasty thing, negative gamma plus or minus square root of gamma squared minus omega squared, what's that gamma thing going to be? Okay, this is really alphabet soup. We got m's, we got p's, we got b, we got k, we got gamma, we got omega, we got 0. Oh my gosh, what is going on here? The short story is that we need to find the roots of this quadratic equation, and this is a template that those roots should be able to fall into. Can we identify the pieces in that template once we shake it out? Okay, so the comfort here is that, can we say this is just a quadratic equation? I mean, if you're at the point where you can say, oh, good, it's just a quadratic equation, that's easy. That's good news. It's in terms of a variable p instead of x, but that shouldn't throw you for a loop. The right side of this template looks like it came out of the quadratic formula or the quadratic equation. Remember, negative b plus or minus the square root of b squared minus 4ac all over stuff. Okay, it kind of is reminiscent of the quadratic equation. And since we're looking for solutions to this equation, it shouldn't be a surprise that the candidates kind of look like something that would come out of the quadratic formula. So we just have to get those two things to work together. And let's not try to jump to conclusions or look too far ahead. That's a trap people fall into, is trying to project to what the result is going to be before setting off on that process. And you don't want to do that. You just want to start trying stuff. So the story with the quadratic formula that everybody knows and loves is that ap squared plus bp plus c equals 0 will have solutions that look like, again, it's not x's, it's p, but that shouldn't matter. It's the variable, right? Negative b plus or minus square root of b squared minus 4ac all over 2a. Everybody's got that, right? So if the generic form of a quadratic with variable p gives us solutions that look like this, what happens when we change our lettering and we're looking at mp squared plus bp plus k equals 0? All right. Well, all we do is, well, what was capital A becomes lowercase m. What was capital B becomes lowercase b. What was capital C in the generic template that everybody knows has turned into little k. All right, so go up here and take your capital B's and turn them into lowercase b's. Take your capital A's and turn them into lowercase m's. And take your C and turn it into little k. So according to this form of the quadratic equation, the quadratic formula gives us that the solution values for p should look like this. Negative b plus or minus square root of b squared minus what would have been negative 4ac over 2a, except with the change in lettering. All right, so if the question was simply find the solutions to mp squared plus bp plus k equals 0, we're done, right? But that isn't quite what the question was. The question was, can we take that answer and put it into a very specific template and then name what the pieces in that template are? But we're halfway done with the battle, right? We have the solutions. Now it's just hammering at them to get them to look like what we want them to look like. Now, this is the template that was presented, okay? Notice that our just quadratic formula answers have denominators, like it's b over 2m there. There's a division by 2m under the square root. But the template that was given in the problem doesn't have any of those denominators. And so that means we have to do some cosmetic surgery on our answers to try to get them to look like this, okay? But what this template is saying, I mean, the gamma and the omega, there's nothing magic about those symbols. They're just spots, right? And so this template says our roots should be able to be put into a form where there's negative something plus or minus the square root of that same thing squared, right? Gamma and gamma. Okay, who cares that it's gamma? It's just the idea that there's something that's going to go in these two spots and it has to be the same thing. That's why it was given the same name. And this omega thing, who cares that it's omega? It just means there's something else being squared in that extra spot, right? So, excuse me, we have to remember what our original solutions look like and decide, can we hammer at it cosmetic surgery wise so that the same thing ends up there and there, right? And something else can be here and it won't really matter because the question asked for gamma or whatever sits here. Okay, so here are the two things we want to line up. Here's our raw answers from the quadratic formula. Here's the template that we need to fill. What's going to go into those red squares? Well, we need to take our answers and make sure that just this whole thing is a square root. It's not a fraction with the square root on top, so that this matches this. This is where some more significant algebra comes into play. This is the worst part of the problem, is just making that cosmetic surgery on our expression. Now, if we look here to here, right, it sure looks like this red square, which was gamma, is going to want to be b over 2m, okay, to make the leading parts match. Can we make that happen over on the right side too? All right, so let's head off on our algebraic journey here. Negative b over 2m plus or minus this term. I'm going to prepare this denominator to absorb it underneath the square root. So I'm going to take 2m and I'm going to write it as the square root of 4m squared. The denominator here is equal to the denominator here, but this denominator is now written so that we can mush it up into the square root on top. All right, and just make one big square root. And then we can split that fraction that's now under the square root and make it a big mess. And then here's a little bit of simplification that can be done. So with cosmetic surgery on our original result from the quadratic formula, we've presented it like this. And now we can match it up to the template that was asked for on the problem. Negative b over 2m, right there, and there. Square root of b over 2m squared, gamma squared, minus, k over m. Okay, great. That would have been tied to this omega, but omega wasn't asked for in the problem. But it sure looks like gamma did end up being b over 2m. Same thing in two spots, just like in the template for the answer. So make sure that you can follow that through and see that gamma is very likely b over 2m. And even though it's not asked for, can you say what omega would have to be to make these two forms match? What would omega look like? That's a bonus question. If I had bonus points to hand to you, I would do it. I don't. So you'll just have to be able to pat yourself on the back. The old Barry Horowitz, if you know who Barry Horowitz was. All right, that's it. This took a lot longer than yesterday's video, but there was a lot more detail. Hopefully in another couple of days, I'll spit out another one.